ญาไม่ปัญญาเราอยู่โรงเรียนวัดทำไมยังไม่ได้นัดทำเองเราอะไรที่บอกอะไรเยอะคอนเสิร์ตในนี้มันจะต่อยกันไหนแต่เราในนี้เอาไปให้กูสิเอาไปให้กูแต่เราในนี้เอาไปอ่ะกูร้อนในนี้อ่ะไม่ถูกนะกูเยี่ยเข้าวันเลยว่ามึงสาวนึกแล้วคนเราได้เหรียญฉีดน้ำหอมเลยที่ได้ฉีดน้ำมนต์เฮ้ยอะไรวะหอมเรื่อยๆเกี่ยวเหลืองแม่เกี่ยวเหลืองแม่เกี่ยวไม่เอาวันนั้นกูไปเซฟเลยไหมกูเจอป้าลูกไม่อยู่เที่ยวซีรีส์จ้าแม่คุยกันไม่ได้รับอยู่ตอนนี้แม่ฝากมาถามว่าโรงเรียนเราเก็บคนหรือเปล่าทำไมนัดวันกันเนี่ยโอ้ยว้าวเฮียว้าวสนามมึงไม่มียืนเลยควายว้าวเฮียเฮียโทษนะญาติเทียมยังพังเลยสัตว์เต้มึงว่าทำไมสนามแม่งไม่เป็นสนามญาติเนี่ยกูอยู่ไม่แดกหรอกนะควายเลยโง่จิ๋หายไอ้เหี้ยควายเลยกูได้ถึงไอ้เหี้ยแม่งไอ้เหี้ยเราก่อนเพื่อนก่อนนะแม่งไปถูเสื้อพอเขาหนึ่งเสื้อเก่งอ่ะโง่ควายโฟกิงทูไอ้เหี้ยไอ้กินเดี๋ยวบ้าไอ้เหี้ยแล้วมันเรียนเยอะเห็นบทเรียนไอ้ใครไปจะตุ่มมีวางแผนทะเลาะวิวาทนะครับแม่เราแชมป์เดี่ยวคนเป็นแค่แชมป์ลูกศิษย์เรือนั่นแหละสนุกอย่างเลยเนี่ยแล้วส่วนต่างคนทำให้เมื่อวานก่อนมีอ่ะโอ้ยแค่ก็จะได้เมื่อเราเป็นลูกสุดท้ายไอ้ความหมายอะไรเอาเลยให้มันหลงมึงเอาฟังด้วยจริงนะฟังด้วยวิทยาศาสตร์เลยตอนนี้พูดเลยได้ครับพี่บอกว่าไม่ใช่กับพี่มอหมดอ่ะไม่บอกที่ไหนไม่บอกให้ผมดูไหนเลยก็กรอก
Test 1 2 3 โอเค
ไม่มองอันนี้เราคิดเองไว้ก่อนพี่ทีไม่ขอคอมเมนต์คอมเมนต์แต่ว่ามันโง่ตรงที่ว่ามึงไม่ให้นิ้วอ่ะแล้วมึงจะให้ชิคไปเลยอ่ะอันนั้นมันยากเลย
Okay, good afternoon everyone. Welcome you to SCI33206 that's Physics 5. แล้วทำไมมันขึ้นอะไรได้ขนาดนี้นะ
โน้ตโน้ต
โอเค Yeah, this is the fourth lecture in the second week of the second semester, 3rd of November. The first person, คณาวุฒิครับคณาวุฒิชยากรครับชยากรแล้วก็ทันวินคนเก่งนะแซ่บนะครับแล้วก็1,700เลยเต็มเขาเต็มเท่าไหร่เต็ม1,600คุณได้1,700เลยเหรอเพื่อนช่วยดันสุดยอดมากเพื่อนช่วยดันณัฐวัฒน์ครับแล้วก็ธนากรครับแล้วก็ทัศน์ครับทัศน์จะอยู่แถวนี้ทัศน์ไปไหนแล้วทัศน์นอนจริงเหรอถ่ายรูปส่งมาให้หน่อยผมขี้เกียจเดินไปดูถ่ายรูปส่งเข้ามาในกลุ่มหน่อยขี้เกียจเดินไปดูครับวันนี้ทำไมคุณอยู่กันเต็มเลยอ่ะปกติต้องหายไปแล้วทำไมอยู่เต็มห้องเลยวันนี้ครับเช็คชื่อเสร็จก่อนเดี๋ยวคุณส่งรูปมาให้ผมดูนะขี้เกียจเดินไปดูครับโอเคเราไม่ต้องไปรบกวนเขากันนะประมาณนี้ครับโอเคเรียบร้อยครับnext one ทัศน์ศิลภพครับอยู่ไหนยกมือให้เห็นหน่อยศิลภพเดี๋ยวเพื่อนบังครับโอเคถอดเสื้อด้วย แล้วก็อันนี้วัดโรดละวีเมื่อกี้อยู่เลยโอเคก็สหรัฐครับสหรัฐคุณสอบอันนั้นว่าไงต้องไปสอบใหม่หรือว่าที่คุณไปสิงคโปร์อะไรตอนนั้นครับคุณต้องไปสอบใหม่ให้คะแนนมันได้เยอะๆหรือว่ายังไงอ๋ออเมริกันเทสอะไรสักอย่างนะอ๋อเอาคุณจะไปยื่นที่ไหนยื่นเพื่อเข้าที่ไหนครับคณะวิศวะอย่างเงี้ยเหรออ๋อให้ได้ครับให้ได้สมาร์ทครับแล้วก็จีโน่ครับผมแดนฟ้าไปไหนแล้วคำกอบจองโอเคครับชยากรเดนิสโอเคครับแล้วก็ปุญญวีครับแล้วคนนี้ภูมินันท์คนเล่นกีตาร์เขาไปต้อนรับเกาหลีเลยใช่ไหมต้อนรับเกาหลีสมัยทัศน์ก็ต้อนรับสิงคโปร์ไปกันเอกครับกันเอกแล้วก็ปิดเคนั่งนี่นะแล้วก็นัทนนท์ที่ไปเตรียมเซตใช่ป่ะเตรียมเซตแล้วก็ทักฤษครับทักฤษโอเคปาธรรมเลยครับแล้วก็กฤษจีจะอยู่แถวนู้นนะกฤษจีอยู่ไหนกฤษจีรับเหมือนกันเหรอไหนคุณยืนขึ้นให้ดูหน้าก่อนครับคนอื่นหรือเปล่าโอเคเยี่ยมมากธนทรครับผมนฤทธิ์ครับผมก็กสิเดชครับผมพัฒดลหันหน้ามาดูหน่อยโอเคครับภูเมศวิบูลย์พวกนี้นะภูเมศกับวิบูลย์ภูเมศอยู่นี่แล้ววิบูลย์ไปแล้วนะโอเคตามสบายครับคุณไม่เล่นบาสตีแบดแล้วเหรอไม่เล่นบาสตีแบดแล้วมีงานเยอะตามสบายครับโอเคas you observe from this sentence, you just simply say that the intensity of the transmitted light is the same for all orientation of the polarizing feather. So it means it has uniform distribution of the polarization axis of the light. And for the ideal polarizing filter, there is no defect. The transmitted intensity will be half the incident intensity. So this is only the text, but from what the students in M604 has asked last Wednesday, I'm going to show you the detail. No one of you would like to know why we get 1/2, right? Where is the pen? Okay, the reason is the following. If you can still ตรงไหนผมลบได้ครับตรงไหนผมลบได้ซีกไหนซีกนี้ครับ ครับหน้าเหมือนใครโอ้มีควันด้วยเหรอเนี่ยไม่รู้วิบูลย์ป่ะเป็นอาจารย์หรือว่าเป็นนักเรียนเนี่ยนักเรียนไปให้ว่าอยู่ห้องนู้นห้องนู้นเหรอใครโรคจิตเหรอครับผมจำชื่อเขาไม่ได้ดิจะพวกกลุ่มพิชานันอะไรวะนั่งแถวๆกลุ่มพวกนั้นปะใช่ปะที่เขามั่วสุมกันเยอะๆใช่ปะ ตอนเรียนก็นั่งเป็นกลุ่มเป็นก้อนอะแล้วบางวันก็มีเอาไพ่มาเล่นด้วยนะอยู่ข้างหลังอะจำไม่ได้ครับเฉลยเลยครับคือใครครับเนี่ยอ๋อกมลทิพย์ตัวนี้ตัวสุดยอดตัวนี้ตัวสุดยอดมากคุณนึกชื่อแล้วได้เลยจำได้เลยอ๋อใช่ชื่อเล่นเขาชื่อครูนะครับชื่ออะไรครับครูฮะครูฮะครูครับเขาอ่านสระอูอ๋อกวนอูอะไรอย่างงี้ใช่ป่ะอ๋อกวนอูอะไรอย่างงี้เทพเจ้ากวนอูโอเคas you can remember the Malus law, right? I is I0 or Imax. Okay, the max magnitude. Imax the maximum value of the cosine square phi, right? And if you want to find the intensity after the polarizing filter, you're gonna need to average value. Okay, take the average value. So. You have the uniform distribution of the possible polarizing axis of the incident light. So probability of phi, the distribution, can be 1 by, because one rotation would cover 2 pi radian, right, one circle. So it's going to be 2 pi. Okay, and you can find I bar, which is the incident, the average value of the incident intensity. So this will be the integration, right, from 0 to 2 pi. Okay, and P phi. Okay, and I, which is a function of phi d phi, right? And you can see that this is only the constant, so we're gonna have 1 by 2 pi. Okay, integration from 0 to 2 pi. ขออนุญาตลบอันนี้นะครับเพราะว่าไม่มีพื้นที่ให้ผมอินทิเกรตสุดยอดมากตัวเด็ดเลยคนนี้ Okay, when you substitute this one, okay, it's going to be only constant 1 by 2 pi, and I phi is Imax, right? You can also move Imax to be out of the integration region, and here you have cosine square. Okay, and phi, d phi, right? I hope that there is no heat problem about the handy. คุณช่วยดูหน่อยนะคราวที่แล้วนะครับมันหลุดใช่ไหมมันตัดไปเลยเพราะว่ารุ่นเนี้ยมันเป็นอะไรกรอบไทเทเนียมอ่ะแล้วมันไม่ระบายความร้อนนะครับพอมันร้อนมากก็ตัดหยุดไม่อัดนะครับทำให้ผมต้องไปรวมไฟล์ยากแล้วมันก็ขาดหายที่เราอัดเนี่ยไม่เหมือนรุ่นเก่า3 ชั่วโมงรวดไม่มีปัญหาไม่เคยมีปัญหาเลย Okay, you can move Imax to be out of this one. Okay, you're gonna get Imax divided by 2 pi, right? And the relation of cosine square phi can be written as you start from cosine of 2 phi. Okay, it's going to be 2 cosine square phi minus 1. Okay, and here we can replace this one by 1 by 2, right? 1 by 2 and cosine of 2 phi plus 1, right? Okay, you move minus 1 to be here plus 1 and you divide by 2. And then, of course, you're going to have here the integration from 0 to 2 pi, right? And 1 by 2 and cosine 2 phi plus 1. Okay, d phi. Okay, and here you can make the integration, right? You can move 1 by 2 to be out of here. It's I max by 4 pi, and you're going to have here integration from 0 to 2 pi of cosine 2 phi d phi, right? And next term is integration from 0 to 2 pi and d phi. Okay, that's it, right? And this one can be 1 by 2, right? 1 by 2. 1 by 2 of psi, right? The differentiation of psi to phi will be cosine 2 phi, right? But we need to have also 1 by 2, right? So this will be I max okay, and divided by 4 pi. And here we have 1 by 2 of psi 2 phi. When your phi is 0 and phi is 2 pi, that's the first term, okay? And the next term is phi from 0 and phi is 2 pi. Okay, that's all. And then you can substitute the limit of the integration. The first term would be, of course, these two terms will remain 0, right? Because sine of 2 pi and 0 will be 0. But this one will be 2 pi, right? So you're going to get I bar as I max by 4 pi, right? 4 pi. And here you have 0 minus 0. One by 2, 0 minus 0. And plus the second term, which is 2 pi minus 0. Okay. 2 pi minus 0. Okay. Then you get only 2 pi, right? And there you get I max by 2. Okay. I max is the incident intensity. So that's why we get half the incident intensity from this average. All right. That's the idea. Now we arrive at the polarization, right? When the light travels through a substance, it moves from an atom to another atom of the substance. It's better if I use the mouse.ฮะเรื่องแสงเรื่องอย่างเงี้ยได้ประมาณแสงครับทำไมครับเป็นเรื่องเวฟนี่แหละครับแสงก็เป็นเวฟอย่างหนึ่งครับโอเคnow we arrive at the diffraction theorem when the wavelength or the frequency of the electromagnetic wave changes with different material or substance. So the time lag caused by the time lag can happen when there is absorption and re-emission from one atom to another atom. So this is the reason why there could be some delay, okay, when the electromagnetic wave propagates from some places to another, from one atom to another atom. And the light also would get effect from this behavior. It depends on the particular structure of the atoms in each material, whether that material is dense or is quite sparse, quite far from each other. The speed of light varies among several media, so it's not the same. Okay, when the wave moves from medium one, okay, the gray one, to the blue one, yeah, number two. Okay, this is material number one. This is material number two. The waves start from the gray one. Okay, you can observe that the wavelength is quite far away from each other, right? Okay, lambda one is quite large. Okay, it's greater than another one. But once this wave moves to the conjunction or the connection point between the first material and the second material, in this case, we can see that the wave behaves in a different way. The wavelength is shorter, okay, and you can see that lambda 2 is less than lambda 1. And there is another index, okay, which is known as diffraction ratio. It's the speed ratio between the speed of the light or the electromagnetic wave in the space, in the vacuum, divided by the speed of the light in that medium. Okay, this is the diffraction index, okay, in1. And it moves with the V1, okay, according to this long or large wavelength, okay. And here you have V2, okay, and it covers less than that, okay, and N2 is the second diffraction index, okay, which is the ratio between the speed of the light in the free space and the ratio and the speed of the light in this medium, in the second medium. Okay, when a ray of the light travels through the transparent medium, it encounters a battery. Okay, it is it arrives as the battery, and part of the ray is reflected, and part of them enters the second medium. Okay, parts of them will be reflected. We consider here only the part that further transmit to the second medium. What you can see is from this actual experiment, this is the laser light, and of course the laser light travels from the air, right, from the air to the lucite block. Okay, this is a kind of crystal material, and part of the light you can see here, it gets reflected from the surface, okay, or the boundary between the air on the lucite block Okay, the component number 2 is the reflection. Okay, you can see that is not the intensity in the second ray is not so strong. Okay, as same as the first component number 1. Okay, and part of that will propagate further through the lucite block. That is a little bit dispersion. Here you can see the beam width of this ray. The width of this ray is greater than the original ray. Okay, and yeah, but anyway, it still propagate through the second medium, which is lucite block. Okay, and when the light travels inside the lucite block, it's gonna meet again the boundary or the connection region between the lucite block and the air. Of course, it's gonna be reflected. Okay, this layer will be reflected and it's moved as the number 4. Okay, component number 4. Parts of that will propagate, but it's not so strong. Okay, and once it goes to along the 4th direction, okay, it's gonna meet again the boundary between the lucite block and the air. Okay, and you can see that the intensity here in number 5, okay, which is the diffraction result, is less than is greater than the component number 2, and you can see a little bit here the reflection in the second round of the refraction, but it's not very light. Okay, not so heavy and so strong. Okay, the ray that enters the second medium is bent at the boundary and it says to be refracted. Okay, we have reflection when it's going to go to the opposite direction, but when the rays propagate almost in the same way, it's going to be called refraction. Incidentally, start from this one, okay, from the air, which has the angle of theta 1 to the normal line. Okay, normal line is the line that is perpendicular to the boundary surface between first medium and the second medium. Okay, one is meets the boundary point. Okay, part of that will be reflected, and this is called reflected ray. The reflected ray can have any angle, for example, theta dash 1, and part of that will be reflected to the second medium. In this case, it's made of glass, and this angle will be theta 2. Okay. From this phenomenon, human has tried to observe how come this relation between among these 3 angles, theta 1, theta 1 dash, and theta 2. Okay, in the first medium, the speed is denoted by V1, and in the second medium, the speed of the ray or the light is denoted by V2. Okay, this is light propagation model under the refraction and the refraction. In figure 37, the angle theta 2, which is the angle of reflection, depends on the property of two media, and on the angle of incident theta 1. Okay, it depends on 2 things. The first one is property of the of both medium. Okay, and the angle where it comes to in the first medium. The relationship that can describe theta 1, theta 2 in speed in the first material and speed in the second material is in equation 12. Psi theta 2 divided by psi theta 1 will be equal to V2 by V1. As the light travels from a transparent medium to another, its frequency doesn't change. Okay, the frequency doesn't change, so if the light can have longer wavelength, it's gonna be able to travel more and more, right? From the typical relation V1 equal to lambda or F and V2 equal to lambda 2 F, we would have, okay, of course, F is the same. We have lambda V1 by lambda 1 as F, V2 by lambda 2 as F. So we can equalize both to each other. F is the same for both propagations regions. But here you can move V1 to the denominator at the left-hand side. You can move lambda 1 to the numerator in the second side on the right side. You're going to get V1 by V2 and lambda 1 by lambda 2. The index of refraction of an optical medium can be called refractive index. It's denoted by N. Okay. This quantity plays a crucial role in geometric optics. The index of the refraction of an optical material is the ratio between the speed of light in the vacuum and the speed of the light in that material, okay, which is denoted by V. Simply speaking, N is C by V. Okay, C is somehow or approximately 3 times 10 to 8 meters per second. Let's have a look at the actual value of several refractive index N. What you can see, if the index is large, so the light cannot well propagate through that material. But if the index is very small, the speed of the light in that material will be quite large, very close to the speed of the light in the vacuum. อ้าวหมดเวลาแล้วเหรออ้าวจริงผมก็ว่าดังแค่ครั้งเดียวไม่ใช่เหรอฮะอ๋อไบรอันมาแล้วเหรอ Brian I'm too late or what โอเค sorry โอ้ตกใจหมดเลยผมก็นึกว่า Okay, if the refractive index is small, okay, or this ratio is small, it means the speed of the light in that medium is quite large. Okay, so it's very close to the speed of the light in the vacuum. So this ratio will be very small. It means that that medium contains a very light, okay, very non-effective atoms, so they can those atoms don't obstruct the movement of the light at all. Okay, and you can see here the diamond, okay, has a large value of the index of refraction or refractive index. So it means the light cannot well propagate inside diamond. Okay, and next one is this is solid. Okay, of course, what we can see is that the solid would have denser molecules, right? So denser particle means it can absorb and re-emit the light quite much. So you can see that most of the index of refraction in the solid case is larger than the refractive index in the liquid case. And if you talk about a gas, okay, is very close to the speed of the light in gas phase will be very close to the speed of the light in the vacuum, because there are very small number of molecules or atoms in the gas phase. Okay, and of course you can compare the air to carbon dioxide. Carbon dioxide is heavier, right? So the heavier molecule would cause stronger absorption and stronger and less re-emission. So that's why you get larger value of the refractive index. Okay, it means the light can be absorbed quite much in the heavy air or heavy gas phase. This one, carbon dioxide and air. Regarding the ice in solid phase, for example, at 0 degrees of Celsius, you're going to get something 1.3 cold. It means the speed of the light is not so good. Okay, it's not the same as the speed of light in the background. Next one is water in liquid phase. You can see that the reflection index in the liquid phase is even worse than in the solid phase. All right. Here is another table of the index of refraction. Ice, okay, 1.309, okay, the same value. In fluoride, CaF2, right, fluoride, 1.434, okay, the same exact value. Polystyrene, we have also log salt, quartz, zircon, and fabulite diamond, okay, diamond 2417. Okay, and lutein. And here we have also glasses in terms of crown or light flint. Okay, flint would absorb more the light. And that's why the light cannot well propagate in the light flint. And lanthanum flint has even higher absorption. And when we talk about liquid methanol would have the refractive index like this. If we talk about if we consider carbon tetrachloride, okay, 4 atoms of chlorine, we're going to have 1.460. Carbon disulfide or benzene, okay, these are examples of the complicated molecule structure. So the light can be much absorbed than the light can be more absorbed in this heavy molecule. This is done at the yellow sodium with the wavelength of 598. Okay, if you make the experiment to different wavelength of the light, you're going to get also different value from this table. Once we manipulate somehow, okay, V1 by V2 as C by N1 and C by N2, you're going to get V1 by V2 equal to N2 by N1. And in terms of wavelength, okay, it's the same. V1 divided by V2 will be lambda 1, lambda 2. Okay, the speed depend directly to the wavelength. So if your wavelength is greater, you can have more speed. Okay, and but it's inversely proportional to the refractive index. Okay, refractive index is large, mean your speed is low. Okay, if your refractive index is small, it means your speed is large. Okay, in the opposite way. Property of geometric optics are as follows. Angle theta A, theta B, and theta R are measured from the normal in this case. If you have the incident ray like this, it propagates from the first medium to the second medium, substance B. Of course, this ray will be separated into 2 components. The first one is reflected component. The second one is refracted, okay, which is of our interest here. Okay, theta A and theta R. Usually theta A and theta R will be equal, usually both are equal to each other. And theta B could be found from the above relation, psi theta 1 by psi theta 2 equal to V2 by V1. Or N1 by N2, okay? N1 by N2. The incident, reflected and reflected rays and the normal to the surface all lie in the same plane. This one, okay? These three layers are in the same plane. The angle of the reflection is equal to the angle of the incident. So usually theta A is equal to theta R. Now we talk about this person, Willem Brought Snell van Leeuwen. The most word that you may often hear, the word that you often hear is Snell. Okay, it comes to Snell's law. He is a Dutch astronomer and mathematician who discovered the law of refraction. Of course, it's known as Snell law. Okay. You can see the ancient person usually have quite complicated name. It has the roots from Latin language. The law of refraction, which was discovered by Willem Brought Snell. In Latin, it's called Willem Bordus Snellius. Okay, the word in Latin. He lived in 1580 to 1624, and this law is known as Snell's law. Snell's law states that if you substitute VA by VB and B by NA from 15 to this ratio, you're going to get psi theta B equal to VB by VA, psi theta B by this one. Okay, you get N A by NB, right? And once you move NB to this one, NA to this one, you're going to get NA psi theta A, NB psi theta B, where both angles are measured from the normal to the surface of the material, A and B. The unpolarized light can be partially polarized by the refraction. This is a 3D diagram. Okay, the plane of incident is the yellow one. Okay, which is perpendicular to the surface here. Unpolarized light means the light that has the electric field axis in any direction. Okay, once it moves to the surface between the air and this material, the reflected one, okay, would get the polarization like this. Okay, the E field is horizontal to the plane of this reflection surface, and the reflected component would have two E field. Okay, the one that is parallel to the refractive index, and the one that is perpendicular to the former E field. The plane that contains the incident and the reflected rays and the normal to the reflecting surface is called plane of the incident. Okay, you can see this yellow plane cover direction of propagation here in these three ways. The angle of the incident is called polarizing angle, theta p. If you choose a proper theta p, the light here will be parallel oriented in the parallel way. Okay, it's called polarization. The light will reflect only when its electric field is perpendicular to the plane. of the incident are parallel to the reflecting surface. This is the plane of incident. The polarized light would have the E field perpendicular to the plane of the incident. And in other words, these polarizing actions will be parallel to the reflecting plane. Here is the incident. I need to make focus. Okay, here is the incident light that has E field in any direction. Okay, and one is hits the surface between A and the second material. Okay, the second material you're gonna have with the angle theta p, which is polarizing angle. You get all the time E field parallel to the surface and perpendicular to the plane of incident. And in the reflecting component, you're going to have polarization in two axes. Okay, the one that is parallel to the surface, and another one is perpendicular to the former one. Here you would have theta p, tan theta p equal to NB by NA, which is refractive index of the second material, and refractive index of the first material, NB by NA. You may ask me why, right? You can see that this is theta p. Okay, this angle would be somehow 90 minus theta p, right? Because this one has already right angle. Let's consider this person, Sir David Brewster. He was a Scottish physicist, and he is best known for his experimental work in optics and polarized light. And this angle, apart from the word polarizing angle, is known as Brewster angle. Okay, which is the ratio between the refractive index in the second material to the refractive index in the first material. All right, and what else? We use this, right? Okay, in 1812, David Brewster noticed that when the angle of the incident is equal to the polarizing angle, the reflected ray and the refracted ray are perpendicular to each other. From this condition, the angle of theta b will be, as I told you, 90 minus theta p. So psi theta b will be psi of this angle, right? So psi will become cosine of theta p. And you can see that in a psi theta a, it be psi theta b. This one will be converted to cosine, and on the left side it's still be psi theta p. Okay, and you can move cosine to the left hand side, and you can move NA to the right hand side as the denominator. And of course, sine divided by cosine will be tan theta p. And we get NB by NA from the former equation. This relation is known as Brewster's law. And that angle is called Brewster's angle. When the tangent of the angle of the incidence theta p equal the ratio between two indices of the reflection, the reflected light is completely polarized. Now let's have a look at an example about sunlight reflection. The sunlight reflects off the smooth surface of an unoccupied swimming pool. It means no one is currently in the swimming pool, so the surface of the water in the swimming pool is assumed to be a smooth plane, but in fact it's not. Assume that the reflective indices of the air is 1. It's actually not 1, okay, 1.0 blah blah blah, but we approximately say that this value is 1. And if the water has the refractive index of 1.33, what angle could make the complete polarization? So it's going to be tan theta p, right, equal to NB by NB. So the refractive index of the second material or substance, in this case, of course, it starts from the air, and the second material will be in water. So refractive index of the water, okay, what is the corresponding angle of the reflection for the light that is transmitted into the water? So when you know theta p, you can find theta b by substituting it from 90. Okay, theta p equal to theta p, and this is theta b, right? Theta b and theta p could be found from, this could be found from the Bristol law, and the angle of reflection will be 90 minus that value. So 90 minus 53 will be 36.938763 degree. And at night, okay, the light, okay, usually in the swimming pool, the owner would install the lights in the swimming pool, on the swimming pool wall, right? And they're gonna open that light or lamp during the night time so that any swimmer can still swim in the swimming pool. So we don't have at night any light from the sun, right? There is only a single source of the light in the swimming pool. That's the light under the water or on the swimming pool floor or ground. So the light will travel back in this direction. Okay, and we're gonna have theta p polarizing angle, and the angle that is reflected or deviated from the normal axis. In this case, the second medium would be air, and the first medium will be water. So tan theta p, right, will be destination by the origin, right? So in 1/133, okay, that's the value of ratio. And if you want to find theta p, you're going to need to use the arctan version. therapy is arctan of 1 by 1 therapy, so it's 36.93 each. And theta B, which is the angle of reflection, could be 90 minus theta P, okay, which is 53.06 degree. Now we arrive at the application of the electromagnetic waves, okay, so that you can see how the electromagnetic wave act on our daily life. The first one is radio or audio communications. You can still see such type of radio station. Okay, it's not completely faded away from our daily life. Okay, radio was the first technology that uses the EM wave for telecommunication. The meaning of telecommunication, as you know, tele, it means something far, right? Sorry. So this is the communication over a long distance. Okay, not a short distance, but communication can cover also short distance. Sound waves enter the microphone and are converted to electrical impulses. And the electrical impulses will be transmitted to the cable line, amplifier, and to, again, the coaxial cable. And then we can get the electromagnetic wave from the antenna, which is transmitted by the radio station or television station. The whole process is the following. When you speak, okay, there is mechanical wave, or simply speaking, it's sound wave. The sound wave will hit the diaphragm inside the microphone, and the diaphragm, when the diaphragm moves, it's going to create the voice, okay? And the voice will be modulated by calibre wave, and later is amplifier, okay? The small impulse will be converted to bigger impulse, okay, like this. And after that, we arrive at the transmitter, which contains the antenna. The antenna will, this signal will be transmitted to broadcasting antenna, and antenna will emit the electromagnetic wave according to your voice. Okay. This is the diagram of the transceiver, receiver in wireless communication or audio communication, in order to pick up the radio wave and then convert the signal back to sound waves. Okay, we start from the left side. That's the symbol of the antenna. The antenna is connected to the bandpass filter, so that we are going to throw away the signal that doesn't belong to our interest. And then you increase the strength of that signal, which is quite weak, but you can receive it from antenna. And they use the modulator, okay, which is somehow like diode, okay. And the signal after we amplify, okay, we increase the strength, and then we transmit it to the speaker, so that you can get very loud music or speech. Another application of the electromagnetic wave is the radar. Radar stands for radio detection and ranging. The example of the antenna with the purpose of targeting an object or ranging is somehow this. It looks like the antenna you can see from at the airplane, right? At the airplane, we would have the same type of the antenna. It's going to rotate all the time in order to search for the incoming airplane. or even the bomb, right? Even the weapon, right? Yeah, that's the radar receiver antenna. Now, in order to use it better or with more flexibility, they're gonna install this antenna onto vehicle, and then they can move this vehicle to be everywhere on Earth. So that if you want to keep this area safe, you have to install this one. And once you know the radar or the rocket, yeah, you can tell the people, the inhabitant, the citizen, to avoid any crash from this weapon or rocket. Radar started during World War II, okay, as the way of detecting the aircraft and the ships from a distance and estimating their locations. But this technology might be too old, okay? It's not of interest or not popular anymore. Here you have radar works. The radar will transmit the electromagnetic wave, okay, the left side, and it's going to hit the target. And the reflected wave or the echo wave will get back to the receiver. Okay, the receiver has the same kind of antenna. They're going to receive the emitted electromagnetic wave. Application of the radar could be found from the monitor in the airplane when you are pilot. Okay, when you are pilot, you need to see is there any airplane in your region? Okay, like this. And today the radar is no longer limited to the military, but it's also applied to commercial aviation, like this one. Like in this figure, they have the system which is called ADS-B. ADS-B means Automatic Dependent Surveillance Broadcast. So you can make a programming in order to act as the captain or the guy who is risky in the airplane. They use the information from the ground system, from another plane, or from even the satellite, okay, so that they can know its own position, or they can know they can get the information or data from other airplanes. Okay, this is ADS-B. Another kind of radar system is that they use this principle to predict the rain. Okay, it's the task which is known as weather forecast, right, or weather prediction. So you transmit the electromagnetic wave. If it hits the raindrop, which is a piece of water, and the wave get reflection. Okay, you can use the speed of that kind of electromagnetic wave and compute you can compute the distance or how far or how much time they're going to move to you. Another possible application of the radar system is that the police can use the radar gun. Okay, they just transmit the radio wave and it hits the car. Okay, and the wave will be reflected from the car to the same position, which acts now as the receiver. Radar gun can be used to measure the speed of the car on a highway, okay, for some regulation in some countries, right? The radar has been applied further for the next apparatus, and that's called microwave. Okay, in the moving figure of the car, they say has different frequency from the microwave emitted by radar gun. Radar led to the invention of microwave oven when you consider this accident discovery by Percy Spencer. Okay. He worked at a company which is known Ratheon. Okay. He just carried a piece of chocolate, okay, piece of chocolate, inside his pocket, chest pocket. And because he works as the radar engineer, he stopped at the radar magneton. Okay, there would be several electromagnetic waves, okay, to his chest, his body, and he noticed that the chocolate bar in his pocket has melted. Okay, and at that, in the same year, he just quit the company and invented an apparatus that can heat up anything, especially food. Okay, and this is called microwave oven. Okay, that's what Percy Spencer did. Here is the resonant cavity that can create electromagnetic wave or microwave or radar wave. And if you let it hit the chocolate, okay, you're gonna get melted chocolate like this. The cell phone is actually a radio transmitter and receiver that uses microwave. Here is the cellular wireless communication. These are base station, and here are handy or mobile phone, right? They can send the information in this cell. When the mobile phone moves to another area, okay, they use the signal from the closest base station transceiver or base station tower. This is 4G base station, and this is the directional link. Here is wireless link, okay, and from base station to base station, there will be ground connection, okay, millimeter base station. The infrared is used as remote control as well. Okay, we can get it from light emitting diode or LED. The infrared usually originates from the sun or fire. We use infrared thermography or thermal imaging for the purpose of fever detection when you have several civilians coming onto the airport, okay, because people from different areas would have different infections, okay, and here you can measure the temperature of a guy, which is 36.8. Okay, we suspect that this guy would have a fever, so we're gonna take him out of the row or the entrance or the arrival port in the airport, so that we can further investigate whether he get infection for some serious disease or not. Passengers arrive or leaving countries can be checked for simple fevers such as colds or influenza, or something more serious by thermal imaging. Okay, you don't have to measure the temperature physically to everyone. Okay, just use the infrared thermography. Infrared thermography can be also used during the night in order to detect the thief or the guy that is not good. Because during the night we have low photon, low light. Okay, so the quality of image is usually not possible for everyone to detect the thieves. So it's better to use the infrared thermography. At least we can differentiate the human body from the typical dark 3. The ultraviolet is used to kill some harmful bacteria in order to keep that fruit longer. This can be done usually, for example, in Australia, okay, when they want to export their agricultural products. Okay, because Australia is quite far from other countries, right? In order to keep their agricultural products well, okay, they need to kill some harmful bacteria. It's called kill foodborne pathogens on certain fruits. Okay, so that when there is no bacteria, their food, their vegetable, the fruit can last longer during the flight or during the shipment by the ship. Ultraviolet is also used for the banknote detection, whether it's real or not. Usually, in order to make the banknote, you need to include something that is special, okay, and one of the things is the bar here, okay, or the number 20, okay. If you use the UV light ultraviolet, you can get the reflection. You can see there is a special note, okay, to the authorized banknote. Many people prefer indoor tanning or sun tanning because the rays of the sun are not uniform and it can cause sunburn at times. So there is a special shop who has the lamp that can create some sunlight. Okay. Physicians may use training device to treat skin conditions such as psoriasis. But the World Health Organization or WHO doesn't recommend them to use for cosmetic purpose. Okay, for example, if your skin is very white, if you want a dark skin, you need to go there to get suntan. Okay, without staying on the beach. Okay, let's go to high frequency. X-ray is usually used to detect or see the damage of your bone, your body, because X-ray can pass through your skin, but they cannot pass through the dense material like the bone. This is the photographic film that is made to a person. Okay. This has different size of film, okay, from the X-ray. Now we laugh at the camera rays that is very dangerous. The camera can kill living cells. If you use it in a proper way, they can kill a cancer cell. We are having to resort to surgery. Yeah, that's safe. That is safe for patient body. Okay, but in order to do that, you need to project the camera ray, okay, and you should get the same intersection point so that that point will be full of energy, and with this way we can kill the cancer cell. Even other parts of the body can get destroyed from this projection, but the cell can recover itself. The cell can recover themselves. Okay, the good cell, but the bad cell like cancer cell cannot repair themselves. Okay, we're gonna get rid of the cancer cell automatically in this case. ZDCam use the camera ray as the tracer to build up the picture of what happens inside the patient. Okay, you need to insert some material that can create the camera ray. Okay, when this material is sprayed inside the human body, we're gonna get gamma ray, and we use the gamma ray detector, this one, okay, and we can see the whole picture of your body, which is inside your body. Okay, we finished the first chapter, electromagnetic wave, and that's it for the first chapter ครับจบบทที่1ครับก็ได้ประมาณนี้ครับเดี๋ยวเรายังไม่ได้ขึ้นบทที่2นะผมไม่ได้เตรียมเลคเชอร์บทที่2มานะครับก็จบบทที่1ไปนะครับมีอะไรเลยผมต้องเขียนชื่อลงชื่อให้เนาะตรงนี้นะครับของฟิสิกส์นะครับก็จบบทที่1ไปดังแล้วหรือยังออดเสียงออดดังแล้วหรือยังครับหมดเวลาแล้วหรือยังครับหมดเวลาแล้วหรือยังเอ่ยหมดแล้วนะผมเก็บของไปนะครับห้องนู้นอาจารย์เขาออกแล้วหรือยังครับห้องนู้นยังไม่ออกใช่ไหมงั้นผมนั่งไปก่อน อ่ะออกแล้วใช่ครับอ๋อได้เดี๋ยวไปครับยกไปเลยครับ